Hello, everyone. Thank you for joining us today, and welcome to another Yokogawa webinar, Identifying and Overcoming Noise in Data Acquisition. I would like to thank you for taking the time to join us today. And just to let you know, our goal in the next 40 minutes or so is to leave you better informed on dealing with noise in data acquisition. Before we begin, I would like to go over just a few housekeeping items. The audio portion of this webinar can be accessed either through the teleconference number provided in the Info tab of your WebEx Manager window or through your PC speakers. To hear the audio through your PC, select the Communicate tab and join the audio broadcast. This webinar will last approximately 40 minutes. Towards the end of the presentation, we will have a Q&A section where, time permitting, William Chen, our presenter, will answer some of the questions received from the audience. If your question is not answered during the presentation, please be assured that we will answer them via email in a timely manner. All questions should be submitted in the Q&A windows or the chat window located in the lower right-hand corner of your screen. Our speaker today is William Chen, Product Manager at Yokogawa. William is responsible for the high-frequency instruments and high-speed data acquisition product lines. William has over 3 years' experience with Yokogawa as an applications engineer supporting our test and measurement products, and has consulted on numerous projects in multiple industries, including renewable energy, power electronics, motors and drives, automotive transportation, aerospace, and more. William has a degree in electrical engineering from Georgia Institute of Technology. Without further ado, I'll hand it over to William for our presentation.
Thank you, Christina, for the warm invitation, and good day, everyone. Thank you very much for joining us for the next 40 minutes as we discuss about the topic of noise and data acquisition. Now, I know this is going to be a very broad topic for most of us, so I'm going to try to squeeze as much information as I can in the short amount of time that we have. So, jumping right into it, please note if you do want a full screen view of the presentation, there is a control button at the bottom corner of the screen, so go ahead and click on that, and that'll help you view some of the information a little bit better. So taking a quick look at the overview, the meat of this presentation, we will be covering 7 of the most common noise sources found in data acquisition. Now, I know that there are additional sources of noise in data acquisition. Some of those we won't be covering, but for the 7 most common types, we will be thoroughly covering these common sources. And you may be measuring, you may be experiencing these in your measurements right now, or maybe you aren't aware that they exist in your system, but hopefully by the end of this presentation, you'll be able to identify them and understand the working principle behind them and how to best deal with them. So again, for each of the noise sources, I'm going to give you an example of what it looks like, first of all. Then I'm going to explain to you why it occurs, and then lastly, I'm going to explain to you the common workaround or how you can minimize its effect on your measurements. So as you can see, we'll be covering the following noise source topics. The very first one is quantization noise. So we'll be talking about vertical resolution, least significant bit, and gain error. The second one is going to be dealing with internal A to D noise. The third one is going to be your power line noise. Then moving along, we will discuss about time skew, how to deal with aliasing noise, common mode noise, radiated noise. And lastly, I'm going to give you a couple of application examples. In this case, we're going to be discussing a fuel cell impedance measurement case that we were able to help a client with. So before I get more in depth into these topics, I do want to give a brief overview of data acquisition and categorize currently the way that it's being used for those of you that may not be familiar with all the different types of data acquisition instruments out there. So I'm going to kind of go over the different form factors you can choose and some of the pros and cons of each data acquisition types. So depending on your application, you may be looking at it by bandwidth. In this slide here, I have, for low-speed applications, I consider this to be the DC to 1 kilohertz range. And this is typically going to be for, your mechanical type measurements. Maybe you have some physical sensors for temperature, pressure, and for maybe for your static loads. Usually you'll find a PC-based or a PC-centric data acquisition solution, and this will be probably in the form factor of a Pixie device or LXI, or maybe even we've been seeing some more commonly used USB-based data acquisition devices. And this is where you'll find a lot of vendors will typically have these low-cost plug-in modules that you will build into a mainframe unit. And each of these modules may have one or several functionalities built into it. And typically you'll find that you have some sort of operating system built into the mainframe of the unit. So the advantage to using this type of data acquisition device is that you usually will have pretty high bus speeds and high data transfer rates. It's good for when you want to deal with massive amounts of data and when you're working with thousands of channels, and it can be a little bit difficult to manage all that data maybe on a standalone unit. So this is where you would use the PC-based type data acquisition system. On the flip side, this type of data acquisition system is also the most sensitive to noise, as we'll discover later on throughout the course of this presentation. So moving on, for higher speed applications where you're looking maybe in the bandwidth range from kilohertz, a few kilohertz to maybe a couple hundred megahertz, you'll find more of these benchtop and standalone type systems. These are usually portable systems where you may need to characterize not only the mechanical performance, but also the electrical performance of the device as well. So this is more of the mechatronics area where you're trying to combine the measurements of mechanical and electrical into one data acquisition unit. And, you know, these systems are usually separated from the computer, so they offer portability, great field use, and they provide excellent noise and isolation immunity. But the trade-off there is that you're typically going to find that these systems are higher in cost as compared to your PC-based instruments. Typically, they'll have less channels where you may be working with maybe just maybe 10 to maybe a few hundred as opposed to a few thousands, for example. And lastly, you have a combination of these two, which is what I call a PC-based external data acquisition device. And this is kind of, you know, your tether type, where maybe you have a mainframe or a chassis type instrument that is controlled by a PC-based computer where the acquisition occurs through the hardware of the chassis unit, but then any sort of manipulation gets done on the computer. Now, in terms of signal types, for the most part, when it comes to data acquisition, most people are dealing with analog signals. So whether it's, you know, a DC or AC voltage into an instrument, maybe you have some conditioned signal such as vibration or pressure, dealing with strain gauges or accelerometer. By and large, this presentation will deal with identifying noise problems in these types of signals and how you deal with them. Now, I don't want to overlook the fact that data acquisition also includes analog output signals. And a lot of the noise topics that we're going to discuss today that affects the analog output, that affects the analog input signals will also apply to the analog output signals. So if you are working with the output of an analog voltage from maybe a DC source or a arbitrary function generator, keep in mind that any, you know, errors that you may encounter in the output of the signal may be due to noise. And lastly, the last two I have on here, we won't get into it too much, but data acquisition, you know, also applies to digital logic signals and digital output signals, and also different timing measurements as well. I'll briefly mention a little bit about timing measurements, but we won't go too far in depth with these details because it does require a little bit more time to do that. Now, noise may or may not be important to you when you're working with timing measurements. Due to the nature of these signals, usually that's not the case. But again, keep in mind, if you are getting incorrect measurements with these digital signal types, you want to keep in mind that noise may be a huge factor in dealing with that. Now, the last way I want to classify data acquisition is by the type of application that you're working with. you'll notice that I classified analog input applications into two categories here. The very first one is your low-speed monitoring type application. Maybe you're trending some sort of temperature or analog voltage signal. And, you know, for the low-speed monitoring, what you'll typically find is a chart recorder or trending type instrument where the input signal rolls from one side of the screen to the other side of the screen. And this type of measurement typically deals with DC or low frequencies as well. And, you know, certainly high frequency noises can affect these types of measurements, but you won't typically find that's the case. On the flip side, the second one that I have is a high-speed single-shot type of application. So these are measurements where you're typically looking at the startup or shutdown sequence of maybe a motor drive. Maybe you're looking to capture some sort of transient or glitch event in your system. Or maybe you are characterizing a device where you need to use the data acquisition to trend the signal over a long period of time, but you may have some glitch event that occurs, and typically these are a combination of the two. So when you're dealing with high-frequency or high-speed single-shot applications, typically what we find is a lot of our clients will be working with repetitive waveform type signals, and in terms of data acquisition, when you have repetitive type signals, these are applications where you're dealing with test stands or test cells. Maybe you're monitoring some sort of engine or vibration type instrument or sensor. So in these applications, data acquisition can be classified as something that is repetitive in nature. Now, on the flip side, when you do have these glitch events, one of the strengths of data acquisition is that you can have these memory blocks, or what we call sequential store, where each capture gets stored in time. And this is when you're looking for maybe a specific event in time, or maybe some condition that you know is some fault is occurring in your testing that you want to be able to capture. So in those cases, a lot of the data acquisition devices on the market today will employ one of these two architectures, whether it's repetitive waveform monitoring in a chart recorder, or maybe you have a memory block which acts more like a scope, and you can save these waveforms over time. And lastly, the third type is high-speed continuous monitoring. We also call this free run mode, or streaming to the PC, first in, first out. And this is basically for systems where you require real-time monitoring of maybe a device or a vehicle in vehicle testing. And these can typically last for maybe a few hours to a couple of weeks. And in these applications, you're not typically looking to capture maybe an event, but you're more so using this to capture all of the data and analyze it when you go back in time. So these are some of the typical applications that we run into when we talk about analog input signals with data acquisition. So moving along, we're going to take a look at our first noise source, which is quantization noise. And as you can see here, I've got a grossly exaggerated example screenshot here. And what you'll notice is with quantization noise, you'll see this banding effect. And this may occur either directly, or if, in this case, if you zoom in a little bit, you'll start to see these discrete stair-stepping effects. So essentially, from one data point to the other, you'll see a drop-off, maybe a very sharp drop-off. And what you'll essentially get is the stair-step effect. And quantization noise most commonly affects low-speed, low-voltage measurements. So typically, that would be if you think of thermocouples, low voltage, if you're trying to measure voltage ripple. It does occur in some high-speed measurements, but that is only in the case where your instrument doesn't have enough bit resolution to resolve the signal. And we'll talk a little bit more about that later. But for quantization noise, what you'll see is most commonly it affects low speed measurements. So what causes quantization noise? Well, to understand that, we have to understand two things here. The very first one is when you're talking about the decimal system, we have what we call counts. And for one digit, we may say that one digit you can count from 0 to 9, and we would say that's a 10-count system. For a 2-digit number, you may count from 00 all the way up to 99. So that would be a 100-count system. So when you're talking about the decimal system, we characterize it typically as the number of counts equals 10 to the number of digits. And this is a fairly common way of measuring something. In the data acquisition world, where you're dealing with analog to digital converters, instead of the decimal system, you have the binary system, which essentially you're dealing with number of bits. So I mentioned it earlier about 8-bit systems, but the way it works is basically for a 1-bit, you can have 2 counts. It can either be a 00 or a 01. For a 2-bit system, you can have up to 4 counts. So it could be a 00, a 01, a 10, or a 11. And, you know, moving along, 3 bits would be the same thing. So the way we classify analog to digital converters is the number of counts equals 2 to the number of bits. So it is an exponential number. So you'll see there for the example that I have, for an 8-bit A to D converter, you can have up to 256 counts. For a 10-bit A to D converter, you have 1,024 counts. So you can see that it's an exponential increase when you go from an 8-bit system to a 10-bit system to a 12-bit system. And what this means is essentially for your full-scale range, let's say you're looking at a signal from minus 10 volts to 10 volts. So for that voltage range, you have to divide the voltage by the number of bits. So in the case of minus 10 to positive 10, as you'll see here in the next slide, what we're doing is we're taking the full scale range and we are dividing it by each number of counts, the total number of counts. And that division is what we define as a least significant bit. So you can think of a least significant bit as the smallest voltage change that can be measured by your system. And so it's a very important topic when you're talking about bit resolution. That also determines the resolution of your measurement. So I've given you a little bit of an example down here at the bottom. The way you can calculate it out is the least significant bit is determined by you taking the range and dividing it by the number of counts. So again, going with the 8-bit example, for a minus 10 to 10 volt range, you're taking 20 volts and dividing that by 256 counts. And so what that tells us is that we can resolve a signal down to 78 millivolts, which is not very great resolution when you're dealing with very low voltage, low amplitude voltage signals. That tells us that our 8-bit data acquisition system can only determine measurements with a resolution of approximately 78 millivolts. For a 12-bit system is what you would typically find in more modern data acquisition units. We see that it's a very exponential improvement going from 78 millivolts down to 4.8 millivolts. So keep this in mind when you're purchasing or when you're looking to purchase a data acquisition instrument, that you want to pay attention to the bit resolution, and that will tell you how small of a voltage change you can measure across. Now, keep in mind, if you are using an oscilloscope to make data acquisition type measurements, usually you'll find that most scopes are using differential or passive probes, and almost all scopes are 8-bit. So in terms of scopes, you would expect your least significant bit to be your quantization noise. So now that we kind of understand what causes quantization noise, how do we deal with it? And if you ask most engineers, the most common solution is to apply a filter. Now, typically this is a digital software filter. And the reason why I say it's a poor solution, if you'll take a look at the screenshot that I have there, in the top waveform, which is colored yellow, you have the original signal with a lot of quantization noise. And so here I'm applying a sharp low-pass filter up to the 88th order, which is pretty high for a low-pass filter. And you can see that even applying the filter, we don't get a good recreation of the sine wave signal. So the waveform on top is your typical noise applied to it, and that's because I used a low bit resolution instrument. But you can see there that if you apply a filter, it doesn't give you a very good solution to this quantization noise. So you may be asking, what's a better solution? Well, the answer to that is we want to do one of two things. The first thing is, if you're looking at hardware from a hardware perspective, you want to decrease the dynamic range, and that will increase the bit resolution. So by lowering the range from -10 to 10 volts, let's say you reduce it down to -2 volts to 2 volts. What that will essentially do is that'll increase the resolution so that you can measure a much smaller. Maybe instead of 78 millivolts, now you can measure down to maybe 10 to 20 millivolts. So that's typically one way of doing it. And keep in mind that quantization noise typically exists even if it's not visually present. We all want the most bits for our instruments, but if that's not a cost-effective solution for you, keep in mind that you can just reduce the dynamic range, and this will help to improve your measurement accuracy. So you can see there in the example that I have on the far left, I have the original signal with the full dynamic range, and as I lower the range from -10 to 2 volts, that does increase the resolution. All right. So the next noise source that I want to go into is AC coupling noise. And when you think of AC coupling, I'm sorry, not AC coupling noise, but AC coupling will reduce the quantization noise. And the way it does this is you can think of AC coupling as a high-pass filter where essentially you're removing the DC component. So in this example here on the left, you have the graph is using the full range, but there you have a DC offset, which is affecting the measurement. Now, if you set AC coupling to on, essentially what you're going to do is you're going to remove that DC offset, and you're going to center the signal right at the 0. And when you do that, then you can increase the dynamic range from plus or minus 2 volts to plus or minus 50 volts. And when you do that, you can utilize the full number of counts to increase that resolution. So think of AC coupling as another way. You have to be careful because most data acquisition devices don't have the AC coupling option. But for more of the benchtop and the PC hybrid type data acquisition devices, they do implement AC coupling as a solution. Okay, so moving on to noise source number 2, we have what we call A to D internal noise. And this noise is typically printed on the specifications, and we will typically look at the accuracy specs of your data acquisition device. A lot of factors go into contributing to the internal noise. This is typically noise that is due to the hardware of the manufacturer. So the biggest components obviously are going to be the non-linearity of the A to D converter itself. You may also have some programmable gain error due to the chip, the A to D block, as well as maybe some thermal effects. So let's say you're running your data acquisition device for hours and weekends on end. Typically, the manufacturer will specify a drift or a temperature error due to running the data acquisition device for a long period of time. And keep in mind also that you'll want to keep your data acquisition device in a fairly stable environment. Now, I know that sometimes that's not always possible. Maybe you have an environmental chamber that you need to deal with. So keep in mind these specs, the thermal and the nonlinearity, those will typically be buried within the data sheet. So you'll have to look out for those and be aware of those accuracy specifications. And you'll notice what I put there, that accuracy specs, it's fairly inconsistent across all the vendors. We want to put our best specifications out there, but in terms of the working environment, there's a lot that can influence the A to D converter, and that in effect will have a big impact on the noise that you see. And so some of the specs that you want to be aware of when you're talking about A to D internal noise, you'll want to look at the accuracy. And in this example, I'm showing you a typical way of reporting that, which is a percentage of reading plus some offset error. So this is your most basic accuracy specs. But again, digging down a little bit deeper, you have other influences on the A to D converter. So this may be maybe the absolute accuracy, the signal-to-noise ratio, maybe the effective number of bits, maybe some noise floor. All these things, can affect the impact of how much noise your data acquisition device is picking up and how much that noise is affecting the A to D performance. So typically, if you're purchasing an equipment, you won't be able to improve it after the fact, but if you educate yourself beforehand, and really you need to make an apples-to-apples comparison when you're dealing with these specs. You'll want to typically choose a high-precision digitizer. So 12-bit is usually the baseline for most engineers working in data acquisition, but we're now seeing the market move towards maybe 16-bit and higher resolution. The second thing you'll want to do to kind of minimize the impact of A to D internal noise, make sure you're working in a stable working environment. I know that's not always possible, but if you can, try to keep it in a vibration-free environment, or maybe where the temperature doesn't fluctuate as much. And lastly, the last thing that you can do is also you can reduce the bandwidth that you're using. Okay, moving along, our third source of noise is power line noise. Power line is probably the most common. We typically see this as a humming or also a pickup. And power line noise can really be either conducted through the instrument that you're using, or maybe a power supply that you're using, or it can be radiated through the environment. So this is EMI noise that we're going to be talking about a little bit later down the slides. And in most cases, the noise frequency will occur at a harmonic of the power line frequency. So the most common ones, in the U.S. is 60 hertz. That's your power line frequency. Maybe in some other countries you're dealing with power line frequency of 50 hertz or somewhere in between. And for aircraft, aerospace applications, you're dealing with 400 hertz as power line. And so you'll see there that I have two signals where, our ideal signal would be the clean signal up top. But what we find in the real world is that we actually have this humming noise that's being carried on the fundamental frequency. So why does power line noise occur? And as I said, it can be either conducted or radiated, and typically, in the case of conducted noise, that's something that can be easily solved. And what the industry likes to use is what's called sigma to delta converters or delta to sigma converters. And so the way to eliminate the noise at these specific harmonics, you know, if for 60 hertz, your second order harmonic would be 120 hertz, and your third order would be 180 hertz. We employ what's called a integration method. And so if you don't have the hardware for that to purchase that sigma delta converter, what you can employ is a moving average, and this moving average is typically going to be a software filter. But as we discussed, you know, software filters are not the most effective, but in these cases, it can be a cost-effective solution if you can't, you know, install hardware onto the motor drive, for example, or if you can't install, you know, onto large equipment these hardware filters. So another thing that you can think of is for noise that's radiated or conducted through the data acquisition device, you want to make sure that your instrument is isolated at the input and the output. All right. The next topic is some of you may not consider this to be noise, but I put it on here as well because time skew can be a very can have a very big impact on the amount of error that you're dealing with. And many acquisition devices, they don't have a way to do time-aligned data. And so one of the common methods that people employ is a pseudo-differential measurement. And what that means is you're taking two passive probes that are not grounded at the right level, and you're measuring across two floating points using these passive probes. And what can end up happening is you can have a time skew. Another way you can see this time skew is if you're working with multiplexing or scanning type data acquisition systems. These typically will have a scanning type architecture where the time skew error can have a big impact, especially if you're dealing or working with power measurements. You know, having a time delay can impact the phase angle difference between the voltage and the current, and that will in turn affect your power measurements. So in terms of multiplexing, what is causing this time skew or this time error? And so there's two things that are going on here. You have your scanning clock, which is you know, the interval at which you're taking these measurements. So for example, you may have a module that has a scan clock of 1 second. And so what that means is you're taking one measurement per second. Now your channel clock could be much faster or much slower than that. And we typically find this on multi-channel systems where you're working with maybe 16 or hundreds of channels on one input module. And one cost-effective way of building that module is to employ this multiplexing technology where you're stepping through each channel and aggregating the data before you display it on the screen. So typically with a multiplexing type instrument, you have one A to D converter that's handling all the digitization of all the channels. And what we find here is that with these types of data acquisition systems, you know, you have definitely a lower cost per channel cost savings, but then at the same time, you can notice that you're not simultaneously sampling each channel. And so if you aggregate the delay across each channel, that delay can really add up, and it can really have an impact on the measurement error that you're dealing with. And so, you know, a more costly solution to that is input modules that employ simultaneous sampling, where you have a separate A to D converter for each channel. And in this type of architecture, you have true independent differential measurements where each channel has its own isolation technology. And when you don't have this time skew error, it can really help out with power applications and making sure that your measurements are accurate. So moving along, our next noise source is aliasing noise, and we also call this fold-over distortion. And the concept is very simple. This noise occurs when you have a higher frequency beyond what you can capture. So, for example, let's say you have a 1 megahertz data acquisition device, and you're working with a signal that may be may have a frequency of 500 kilohertz, but then you have some switching frequency that's much higher than that. What you'll find is that higher frequency signal will actually fold over to the signal that you're capturing. So to kind of break down this example a little bit further, I want to go back to a little bit of the basics describing the time domain and the frequency domain. So any analog signal is actually consisted of a series of sine waves that has various amplitudes, frequencies, and phase. And when you break it down, if you look at the frequency domain, you'll notice that each time domain signal can be represented by multiple frequency signals with a maximum frequency amplitude. So essentially what I mean by all this, to give you an example, what this looks like, the red trace here that you see is the actual signal. So this is a signal that we're trying to measure. The green dot is the signal the green trace is the signal that we capture on our data acquisition device. So you can see here for a waveform where we're sampling at 20 samples per second, and maybe the frequency of the signal, for example, is 1 hertz. So for a 1 hertz signal, if we sample at 20 samples per second, that's 20 times the sampling frequency that we have. And so you can see that we can get a good, nice, accurate representation of the original signal. Now, let's say we reduce that. Let's say we're only sampling 5 times the frequency. So again, this is a frequency of 1 hertz, and we're sampling at 5 times that rate. You'll see that we still have a decent recreation of the signal. Maybe if you have some linear curving or interpolation, you might be able to connect the dots a little bit better. But if you're doing a linear interpolation, you can see that while we do get a good overview of the signal, it's not going to be very accurate, and it's not going to be giving us a good resolution in terms of our measurement. And so the last example that I have down there is kind of exaggerated, but if you sample at twice the original frequency, which is the Nyquist theorem, you'll see that we don't get a good picture of the original signal at all. So what aliasing will look like is, let's take the previous example, and again, the red trace is your 1 hertz signal, and your sampling frequency is at 16 samples per second. So still adequate, still 16 times, which is good enough. And you'll see that I've marked there on the yellow line, you know, both waveforms in the frequency domain we captured at 8 hertz, okay? So at 8 hertz, we don't have any aliasing effects. Now, let's say we change the sampling frequency. So instead of 16 hertz, now we're sampling at 8 hertz. If we change the sample rates into the frequency domain, essentially what we have is a 7 hertz signal that we're trying to sample at 8 hertz. And so there might be some noise above 8 hertz that won't get folded on to the original signal. But if you look at the very last example I have, where you're sampling at the Nyquist frequency, or 2 times the sample frequency, what we would expect is a flat line because we shouldn't be able to capture anything above 8 hertz. But in actuality, what we see is that if we increase the frequency, what ends up happening is the higher frequency components will actually start to fold over and appear on the low frequency side of the capture. So again, here's another example. Maybe you have a 3 hertz signal or a 50 hertz humming noise on there. So for a 3 hertz signal with 50 hertz humming, what we expect is an alias noise at 5 hertz. And the reason why this happens is because, for example, in this example, we're sampling at 55 hertz. So if you take half of that in that formula, it calculates out to 5 hertz. So at 5 hertz, what we end up seeing in the frequency domain is an erroneous spike pointed out by that red arrow. And that's noise that will appear as a false measurement, and you may think that it's an actual measurement, but in actuality, it's just noise affecting your signal. But what happens if we don't know the maximum, or what if we don't know the high frequency content? This is typically the case in sawtooth waveforms, where maybe you have infinite number of harmonics. If we don't know what the maximum is, what will happen? And in that example, going back to it, if you sampled at 20 times the rate, the result is that any higher frequencies above that will get folded onto the lower half of the signal, and that will really increase the noise floor and contribute to the RMS measurement that you're making. So really the only way to deal with this type of solution is to implement a hardware filter that filters, it's a low-pass filter that eliminates the fold-over distortion. And this is especially important if you're working with sound, acoustic, or vibration type measurements. You really need the anti-aliasing filter to preserve the phase characteristic of the signal. And so this hardware signal has to occur before the signal is digitized. And essentially what you're doing is you're restricting the bandwidth of the signal. So you're essentially applying an analog filter to the original signal, and that will have an impact of giving you the correct measurement at the right frequency. If you try to implement a software filter after the fact, it's not going to be effective because essentially all the aliased noise will already be in the original signal, and the software filter won't be able to detect that portion of it. Because again, this is a low-pass filter, so the alias noise will show up in the low frequency domain. So as a rule of thumb, we'd like to suggest if you can't purchase an anti-aliasing filter, the simple answer is to just oversample. And a good rule of thumb is to choose an instrument with a sampling rate of 4 times the maximum frequency that you're trying to measure. Obviously, we'd like to have, 10 or up to 20 times, but that may not be a cost-effective solution. So to do that, just, pick an instrument that can oversample at 4 times the rate, and that will be good enough to eliminate some of the anti-aliasing noise. You can also try to sample at a smaller rate and choose maybe a special type of interpolation to kind of connect the dots a little bit better in that last example. But that's not always a guaranteed method, and again, it's difficult to calculate the accuracy in those cases. All right, the sixth type of noise is common mode noise, and for common mode noise, I've given you 3 examples. For a signal with no common mode noise, this is our baseline signal at the very top. If you have a signal with common mode voltage or common mode noise, and let's say you're implementing a pseudo-differential device, what you'll end up seeing is that the signal will be clipped at the very top. For the third signal type, where you are measuring common mode voltages with isolated equipment, you'll have to look at the common mode rejection ratio specification. So what you may end up happening is you may have the original signal, but maybe the lines are a little bit thicker, maybe there's a little bit more buzzing or ringing, and so pay attention to that. If your signal doesn't look sharp, it may be that the instrument that you're using doesn't have a high enough common mode rejection ratio. And then if you're using an instrument with more common mode noise than what the instrument can handle, you're not going to get any good signal at all. So that's the most easiest and most obvious one to detect. So the reason why this happens, the most basic way is common mode noise occurs when you have a voltage difference between the sensor ground and the instrument ground. And as I said before, common mode noise will typically show up as a voltage, and that voltage difference can have a huge impact, can even damage your measurement hardware if you're dealing with sensitive equipment that is not able to handle large voltages. So the noise will go back into your instrument or into your sensor as a voltage, analog voltage, and that's what will damage the equipment. It's a very costly mistake to happen. And some examples of where common mode voltage occurs: if you're making thermocoupled measurements across power devices, so these are devices that have different power supplies across different locations. If you're trying to make thermocouple measurements there with a instrument that doesn't have isolation technology, you could be running into common mode noise there. Any type of battery or fuel cell testing, if you're working with multiple external power supplies, or if you're trying to measure a floating measurement in a noisy environment, that can all come back as common mode noise. And so two things that are happening here. Common mode noise is typically classified as just noise itself, and then you have normal mode noise, which can be the actual signal plus the noise. So you'll see there in the left-hand example, common mode noise is across the device that you're trying to measure and the instrument, whereas normal noise can be that power line noise in addition to the instrument and the sensor. Now, another thing also too with common mode noise is ground loops. And ground loops occur also when you have two different reference ground points. And so an easy way of knowing if you have a ground loop is three ways. Typically, you'll notice some humming or some high-frequency oscillations in your signal. That typically is a good indication that you have a ground loop. If you experience any high energy transients or maybe some inrush, that could also be caused by ground loops. And ground loops can occur, between your three-phase power distribution systems. So if you're working with multiple power supplies, that noise can be injected into the power supplies, through the power supplies, into your equipment. So the easiest solution is to implement an isolation barrier, and that isolation barrier will prevent the ground loop, and it will negate the common mode voltage from going back from your instrument into your sensor. And it's also a good way to keep your end user, your engineers safe, because if you're dealing with very high common mode voltage, that voltage could be hazardous. And so creating this barrier will isolate you from those impacts and prevent the noise from affecting your measurements. So there are different built-in isolation system architectures. I just want to briefly go over the four common types that we have here. The first one is channel-to-ground isolation. Then you have module-to-module isolation, where one module is isolated from the second module. You have your channel-to-channel isolation system, where each channel has its own A to D converter. And then the last thing is you have a specification for maximum withstand voltage. So that's also a insulation type barrier. So for channel to earth, you have typically an isolation barrier across the outside chassis of the instrument, and this is the easiest one to detect. This will prevent you from harming yourself if you touch the instrument, and so you won't experience that shock. The second one is module-to-module isolation. A lot of you are familiar with hot swappable instruments, and this is the reason why we have that is because of channel-to-channel isolation. And this prevents any crosstalk noise if you're dealing with temperature measurements where you have a scanning type or multiplexing type module. A lot of the times what you'll have is some crosstalk noise. And so the way to deal with that is to locate a module that has channel-to-channel or module-to-module isolation. So again, the channel-to-channel will prevent you from having those types of issues. The last type of noise that I want to get into, probably the one that everyone thinks of the very first time, is radiated noise. And this is noise that can occur throughout your facility in the air. And in certain types of environments, especially if you're dealing with manufacturing or industrial type facilities, or maybe you're dealing in a high power laboratory, you'll have a lot of these electromagnetic noise sources emanating through all the different devices that you're trying to measure. And the radiated noise will typically manifest itself as either the common mode noise that we talked about earlier, or it will appear as a combination of both the normal power line noise as well as the common mode noise. And so in order to reduce this, there's two ways. The very first way that most people commonly refer to is shielding your equipment. So this is shielding not only the instrument chassis, but if you've got a rack or test system, you'll want to think about putting or installing a metal shielding across the entire system. And this will help to maybe eliminate, but certainly reduce the effects of EMI noise. You'll also want to pay careful attention to the cabling that you're using. If you have any exposed cabling, maybe it's an exposed alligator clip, a metal alligator clip that's exposed, or maybe you've got a twisted wire pair that has some metal exposed. These are all cases where that metal can pick up EMI noise, and that noise can translate to either common mode voltage or normal mode noise. And so not only do you want to shield the instrument, but you also want to make sure and take care that you shield the cables that you're using. So you typically want to avoid maybe ribbon cables or unshielded terminal blocks. Make sure you have plug-in boards that use high-density connectors. And again, maybe it may be plastic insulation or metal insulation, but make sure for the instrument that you're looking towards that it employs some sort of isolation barrier so that you're not picking up noise from your instruments. Another costly or another impactful way is to eliminate all of these types of noise is to pick a digitizer that can really oversample and provide high resolution. So essentially for quantization noise, you want to pick a high resolution A to D converter, maybe a 16-bit or 18-bit that can provide you a good number of counts. For dealing with common mode noise, you want to implement a isolation barrier, either in between the instrument and the sensor, or across the sensor, or one or both. For power line and aliasing noise, it's best to implement a hardware filter. These are low-pass filters or anti-aliasing filters that can be installed directly onto the signal source itself. and you know, you can read through each one of those, but basically you want to take care of all these things when you're dealing with that. So lastly, I want to get into the application example. In this case, a customer of ours was measuring a fuel cell impedance, and so in this example, I'll show you here on the block diagram. For this fuel cell, the customer wanted to measure the DC voltage, but he was experiencing a AC voltage ripple on the DC signal. And so in order to deal with not only the noisy environment and the AC ripple and all those things, the key requirements I've listed out here that was considered was not only isolated outputs but isolated inputs as well, having a high resolution 16-bit AD converter, making sure that there's AC and DC coupling to remove that offset and really increase that dynamic range. And across that many channels, you really want to implement a simultaneous sampling system so that you're getting the least amount of time skew error. So one of the solutions that we implement here at Yokogawa, we have what's called the Scope Quarter DL850E series, which implements the 4 types of isolation systems that I talked about earlier, which is namely channel-to-earth isolation, channel-to-channel isolation, and module-to-module isolation as well. So we really have a good mix of isolation and A to B converter, 12-bit resolution to give you that good dynamic range as well as that good isolation barrier. So an example of this is when you're dealing with a pulse signal, if you don't sample enough, what you can end up happening is in that lower screenshot, you have this stair-stepping effect, which is that quantization noise. But if you're capable of oversampling or having a higher bit resolution, you can really eliminate that stair-stepping effect and improve that recreation of that original signal. And lastly, you know, we also have a combination of the two, which is the SL1000, which is a PC-based external device, but it's also a standalone system. So it takes the best of both worlds. You know, you've got the high voltage 1000-volt RMS isolation, and you have the flexibility of high data transfer rates to the PC. And these are just some of the solutions that we have to offer. Many companies also offer a PC-based solution as a very cost-effective way, but for really the best performance and really the most precise and accurate data, you want to look for a system that employs a built-in isolation and a good oversampling method to accurately capture that signal. So in summary, I hope I've kind of covered this topic in good detail. We've taken a look at some of the most common noise sources, why they happen, why they occur, and some of the ways to really eliminate and reduce those noise effects. So unfortunately, we've run out of time, but I do really sincerely thank everyone for taking the time to attend this webinar. Although I did receive several very good questions during the presentations, I'll be sure to answer these questions via email. Also, please be on the lookout for a copy of this presentation. It will be available for full download in your inbox shortly. And as always, if you have any questions, you can contact us at webinarwednesdays@us.yokogawa.com, or you can visit us at the web at tmi.yokogawa.com. Thank you very much for attending, everyone, and have a good day.